बाय तो x plus i में यूनिट्स क्या है प्लस माइनस 1 और प्लस माइनस i है। ये चेक करना काफी आसान है। यू यूज समथिंग कॉल्ड द नॉर्म ऑफ एन एलिमेंट। यू से दैट द नॉर्म ऑफ x plus i is x squared plus y squared. ठीक है, make this definition and you show some multiplicative properties so that you can get this. It's not a problem. So in general, x plus i and x minus i must both have this form. Okay. So let's assume that alpha is equal to some m plus n I.
Alpha is an element of.
Alpha is an element of this Gaussian integral. Fine. So what is alpha squared? M squared minus n squared plus 2mn I. Again, this is equal to u times this is equal to x plus I. Therefore, x is equal to some unit times m squared minus n squared. So let's say the unit is, if it's plus minus 1, it doesn't matter because m or n goes switch. So positive मान के चलो. Let's say use 1. If you use 1, then x is m squared minus n squared and y is 2m. और अगर iota है तो बस y m squared minus n squared हो जाता है और x 2mn हो जाता है. So it's essentially the same thing. So we have plus minus this, plus minus this. Okay.
We can find x and.
We have found all possible Gaussian integrals. So to ensure that it is primitive, all you need to do is ensure that m and n are relatively prime. Yeah. And not both odd. क्योंकि अगर both odd होते तो the squares would be odd and their difference would be even. And this is even, this is even. So again, that is a contradiction. So we want the GCD to be 1 and m n not both odd. Not both odd. That's it. You have managed to find all possible, all Pythagorean integrals. So the final solution is given by x equals plus minus m squared minus n squared, y equals plus minus 2mn, and z equals m squared plus n squared.
Yep. We were able to do this because x and y are itself in that ring. Because of that, like suppose if we have some other ring in which we don't have x and y, then like how does we get the idea? मतलब why we are like taking Gaussian integers? You can see the factorization.
Yeah. So the idea was to move from this sum to a product. If you could factorize this into a product, you have a product here, you have a product here. Now you can talk about when a prime divides here and when a prime divides there. Okay, what is the appropriate ring to factorize this in? The question becomes that now. Okay. So this is a sum when you view it as integers, but when you view it instead sitting inside here, it is just an element as a bunch. X plus y, it's an element of it, so it has a factorization. So once you have a factorization, you are looking at this product as another product. So that was the key.
Gaussian integers छोड़ के ऐसे और भी कुछ होते हैं जिसमें एडिशन को हम फैक्टराइज कर सकते हैं। हाँ,
जैसे हम x cube plus y cube को इसमें फैक्टराइज कर सकते हैं using the cube root of unity. जैसे
But is it possible for any other square element?
Sorry?
Can we just find minus under 2 and it work?
So
Can we find another I dash, whatever I dash is my under the minus 2 and will it be the same like this?
under root of minus 2, why would you want to do that?
Like just another possibility.
But why would you want to do that for this problem?
But not for this problem, a possibility as a generalized.
Are you asking whether that will be a ring?
Yeah. I mean Z under root of 2.
You are asking whether if I adjoin
Yes.
under root of minus 2, then it will be a ring? Yeah, it will be a ring.
This is 2y. But that is the same, like, no.
Actually, not necessarily. Not necessarily. It will not necessarily be the same thing. And what are all elements here? It will look like something plus a plus b square root minus 2. This is what it's going to look like. So it's not necessarily the same. Fine. The other proof that which is of importance that we use the same idea. We try to show. मैंने पिछली बार क्या किया था? फोर्थ क्लास के लिए किया था क्या?
पहले फोर्थ के लिए या फिर थर्ड के पहले थ्री के लिए क्या था? थ्री और फोर्थ के लिए अलग-अलग किया था।
और मैंने फोर्थ किया था।
थ्री को एक अलग केस लिया था और उसके बाद फिर
हाँ। तो फोर्थ वाला पार्ट के लिए मैं छोड़ देता हूँ। और
भैया मेरे पास है।
समझ में फोर्थ बार किया था मैं दिखा था कि थ्री गलत कर रहा था।
हाँ।
भैया
हाँ।
ये लीजिए।
अरे कोई बात नहीं, मुझे बस ये जानना था कि हुआ था कि नहीं। तो मैं छोड़ देता हूँ वो फोर्थ वाला। The thing is you use whatever we have learned here to show that Fermat's theorem fails for x power 4 plus y power 4 equals z power 4. You can show that. और मैंने लास्ट टाइम शो कर दिया था। आज के ऊपर Fermat's theorem ठीक
ये भैया कंसर्न में स्कूल के बच्चे
सही बता।
9 उसके अलावा तो समझे नहीं कैसे समझेगा
हाँ अरे नहीं बोला था So this side will apply what?
कैमरामैन भी
So easily take another 20 minutes. So मुझे बार-बार रेफर करना होगा वहाँ से. So later on, if you're interested or in any idea when the maths is not running very hectically, then I can maybe show the proof for any good school. Let's instead move for the case when n is any odd prime. ये क्लियर है ना कि अगर मैं सारे ऑड प्राइम्स के लिए प्रूव कर दिया कि फॉर्मूला शास्त्र सच है, तो मैं और 4 मिलकर मैंने प्रूव कर ही डाला, तो मैं सबके लिए प्रूव कर दिया. ये दिख रहा है because if you have some x power n plus y power n equals z power n की solution है and p is a prime which p is a non prime which divides n, then you can write this as x power n by p whole power p is y power n by p whole power p equals z power n by p whole power p, and these are all integrals. So you have actually found a solution for the case p, but you already have proved that there is no solution for case p, so there is no solution for case n as well. So if you prove for all odd primes and you have finished proving for 4 as well, then you have finished proving for Fermat's last theorem for every positive natural positivity. So now, assuming that I have already done it for 4, let's look at the case when n is an odd prime, x p plus y q equals z.
One small question. Fermat wrote it down and has a proof for it, but what is the indication behind the fact that for all powers greater than 3, you will not have such a, for all integer natural number powers of greater than 3, you will not have such a solution.
Intuition. Possibly he did some calculations and he found an intuition.
There should be something which specifies that yes, this is the one which does not give us this directly.
पता नहीं.
I think you should ask Fermat.
ऐसा नहीं.
He even wrote that he has a proof for that theorem, but we don't know actually what was that proof.
But what is something which was not
Suppose I asked you whether something is true, then you would try to work out different cases and see what happens.
Proof short, but then
It is also some cases. It was done by the.
Look, anyway, you have not done this, you have not done that. Then what have you conjecturing without keeping your foot in either place? Whether you try something and then you see that you're not getting any solution.
Like whether the proof was there or not.
Does this theorem have a proof in number 2?
Which one? Thomas asked.
Possibly said
Like we are trying these methods.
Yeah.
So does this necessarily give us some proof of that, or we have only Weil's
there,
proof?
then definitely that's proof.
There are, I think, two proofs currently of Fermat's last theorem. So one is using by Andrew Weiss. I think Andrew Weiss proof is not non-number theory, because he uses advanced techniques, but they are still from the theory of elliptic curves and model forms. So that is also intimately connected with the theory with number theory.
I'm asking about this.
So I think you already know this, but I think you can mention it for everyone also. There is something called the ABC conjecture. ABC conjecture. ABC conjecture. The reason is it contains some things which contains terms which look like A, B, and C. And it says something about
The mathematician came, right? French guy.
the guy who actually conjectured this came to ISL Bhopal.
Joseph Osterley.
Joseph Osterley. Siddharth Sarkar, he invited him to create. Apparently, he was his person, which is great.
We could not meet him because of his. I don't.
My dad.
So the ABC conjecture is possibly one of the most important number theoretic conjectures currently floating around.
Conjecture.
Conjectures, yes.
perfect number also
It's not important. Of course, it's been around for a very long time. It's not important. It doesn't have ramifications in many areas of everything. But ABC conjecture is not.
ABC conjecture I think got proved, no?
But you don't really work towards it. There are many such things.
Can use
For instance, that P not equal to
It's under D.
because it's not practical.
तो हाँ क्या
ABC conjecture है क्या?
इसका बहुत कॉम्प्लिकेटेड स्टेटमेंट है उसमें एप्सिलॉन और बहुत सारे चीज़ें आते हैं तुम पढ़ सकते हो बुक में क्या नाम है उसका
मिलेनियम प्रॉब्लम्स का बुक
कौन सा?
पढ़ो
ऑनलाइन मिल जाएगा।
Millennium का
एलिमेंट नहीं नंबर
हमारे
थर्ड
इसमें
नंबर चोरी
लाइब्रेरी
मेलिन भी एथेंस है
ट्राई कर देगा, पता नहीं कुछ होगा।
मेरे पास पढ़ा है
कुछ ही होते हैं।
नहीं प्रूव नहीं हुआ है
1 million के
तो conjugation क्यों होता है?
There will exist x cube plus y cube plus z cube equal to w cube such x, y, and z and
the movie recording and stuff.
there exists x, y, and z and w cube that they satisfy such an equation.
X, Y, Z, W.
That x cube plus y cube plus z cube is equal to w cube.
There was a conjecture by Euler actually on this regard that if you have nth power, you need at least n nth powers to do that. It was disproved by Noam Elkis. He used a computer software to actually find a huge solution, counterexample to that and something like
First is
5 8 7.
मैं मेरा क्वेश्चन वो दूसरा प्रूफ भी है क्या एक और
किसका?
इसी फार्मास्यूटिकल का
एक और है, I think. They used some more similar techniques to Andrew Wells to provide a different kind of approach and prove a sufficiently strong theorem to apply Fermat's Nasty. मैं भूल गया था exactly क्या था वो.
But through
But
the
there is no simple.
through the ABC connector it
So
implies
the ABC conjecture, yes, the ABC conjecture does imply Fermat's Nasty as a very simple corollary, but the ABC conjecture itself is a pretty tough conjecture. Formulated by Maser and Oysterley.
So you were asking that whether the cube of 3 would be written. So my question is, how many terms squares do you need so that every natural number can be represented as the addition of those squares?
Where is your equal?
That is a question.
मेरा इस बार का समझ नहीं
अच्छा
Very nice.
I did not think of that.
means how many squares do you need such that every natural number can be represented as the addition of those, as those that number of squares.
Yeah,
This
going
is
to
also
the
a
bottom.
conjecture, like 3 or 4.
So it's solid, means then what do you do?
Still लगेगा ये ऐसा होता है। Still लगेगा ये ऐसा है। 3 2 लगेगा।
को कोई भी नेचुरल नंबर दे दो उसको सम ऑफ स्क्वायर्स करना है, ठीक है? किसी नेचुरल नंबर
Actually, 1 square 1
स्क्वायर ऑफ
बहुत एक पावरफुल चीज़ है पता है 1 square से 1 होता है मेरे ख्याल से पावरफुल चीज़ है ये सब बारे में
तो तुमको ऐसे कितना काम
Make
लगेगा?
any natural or like if you have question क्या था how many squares you require?
हाँ, see like
Make
if
any
n
natural
is equal to a square plus b square plus c square plus d square blah blah blah, तो ABCD कितने लगेंगे तुमको डिस्टेंस?
How can you express a natural number in the
So we can take
how many terms?
And by the way, how many
when
when
you
you
can
want?
one we can have one but
You can use one as number of times you want.
और 1 2
so we can always okay you are asking minimum
That's very good. तो repeat भी नहीं कर सकते। नहीं repeat नहीं।
कर सकते हो, मिनिमम चाहिए बस।
तो उसको दो गिना जाएगा।
नहीं ये क्वेश्चन जो ये हमें मॉडल सर ने बताया था क्या वही
It's a very famous
Nice
thing.
को लिख दिए।
जो भी जितने के number चाहिए ना minimum, it's called that number square.
Square square।
If it's let's say k, it's called the k
ये
square.
वही गिन रहा है उसको।
केस
See,
Was first proved by
plus 0
Lagrange.
plus 0 वो सब
एग्जांपल दे रहा था ये कोई रिपीट कर रहा है।
Yes, it was first proved by Lagrange.
कर सकता है पर मिनिमम चाहिए, मिनिमम
और हम
नंबर ऑफ
लोग
टर्म्स।
जो वो पढ़ाते हैं
Distinct terms. Minimum number of distinct terms.
डिस्टिंक्ट की जरूरत
Distinct जरूरत नहीं है।
डिस्टिंक्ट की जरूरत
So you want length of that?
तुम one को कैसे लिखोगे?
Huh? One
चाहिए।
1 square
One square.
And
एक term
जो सेट यूज नंबर यूज कर रहे हैं।
ठीक है 2 को कैसे लिखोगे?
कोई भी हो सकता
One
है।
square plus one square.
तुम रिपीट करो.
So you want the length like.
हाँ
मिनिमम
Minimum, maximum the one.
जीरो
So that is not maximum. To maximum infinite कर दिया तुमने.
1 plus 0 0 0 0 0
क्या नहीं है
कुछ लोग कुछ कंट्रीज में नेचुरल नंबर्स को नंबर से किया जाता है।
Yeah,
पेरेंट्स नॉर्मल 0
include zero. Makes it very fundamental things.
The thing called as whole numbers.
Same as that.
नहीं नहीं है ना चार
Bhaskar sir.
चंद्रशील भागवत सुना हुआ है।
फोटो में दिखाया था ना homomorphism बोला, never mind.
Never mind. If you know what such words mean,
एकदम confident था, पता नहीं क्या चालू हो गया. Oxford dictionary.
मुझे अभी भी नहीं exactly समझ में आया.
पॉइंट जहाँ पे नॉन डिफरेंशियल
Okay, वो समझ
तो ऐसे लेकिन मुझे शायद श्योर नहीं है पॉइंट अगर मान लो इंफिनिटी पे जाए इसका तो शायद वो भैया को बताओ
इसके बहुत सारे प्रूफ्स हैं. एक ज्योमेट्रिक है, एक
कौन है हाँ वो अच्छा लेना
आपसे कौन बोल रहे हैं?
तो क्या कहता This was the main steps. I'm skipping something which I'm reading. Okay. तो क्या कहता Let's say x bar b plus y bar b equals z bar b. Let's say x bar b plus y bar b equals z bar z. Now there are two cases. Either p divides none of x, y, z, or p divides exactly one of x, y, z. Do you see that if p divides 2, then p must divide all 3? That's obvious, right? P divides 2, it must divide all 3. So then we have contradiction. It's not a good one. So we only focus on case 1, ignore case 2 for now. ठीक है ना? So इस case में first let's take 3. If x cube plus y cube equal to z cube and p does not divide, that is 3 does not divide anything. It's actually very easy to show this. Simply look at this modulo 9. Any cube where that thing is not congruent to 3, अगर तुम उसको क्यूब करोगे तो फिर तुम्हें प्लस माइनस 1 आएगा. तो यहाँ पे प्लस माइनस 1, यहाँ पे प्लस माइनस 1, यहाँ पे प्लस माइनस 1, कभी हो ही नहीं सकता. कोई भी कॉम्बिनेशन लो तो या तो 0 आता है या -2 आता है या +2 आता है. फिर से प्लस माइनस 1 नहीं आता. So this is not possible. Done. Case 1 of Fermat's last theorem for p prime. Done. Now again case 1 for p greater than 3. ठीक है? What will we do? Let's factorize xp plus yp in the pth roots of unit. The ring containing the pth roots of unit. So do you see that this factorization is exactly this? दिखाना पड़ेगा. नहीं देखो क्या करना है. Think about t power p minus 1. This is, how can you write this? Definitely all the roots of this are the powers of the pth root of unit. So this is nothing but t minus omega
5p
omega square. सही करोगे? t minus 1 से चालू करना चाहिए.
t minus 1
omega up to t minus omega power p minus 1. सही करोगे?
p minus 1
ठीक है. Now put t is equal to minus x by 1. तुम्हें ये आएगा. चलेगा? So then this you written as z bar p. ठीक है? If this is a UFD माने unique factorization domain, then it's easy to show that this is true. I think this also I showed last time, but we can leave it for now. Point is, if it's a unique factorization domain, you can show basically that they are all relatively prime, which means that each of these guys must be some unit times
unit times of
unit times of alpha bar p, where alpha is in this ring, alpha is in z adjoint omega. Omega is e power 2 pi by p. Sorry. Moreover, we can also show that if p doesn't divide, if we are working this case 1 scenario, p doesn't divide any of x or y, then it's simple to show that x must be congruent to y modulo p. ये भी मैं दिखा दे रहा हूँ कैसे करते हैं, पर ये दोनों काफी सिंपल स्टेप्स है. टाइम मिले तो पता लगेगा, है ना? But if x is congruent to y modulo p, let's again rewrite this as x bar p plus minus z bar p equals minus 5 bar p. I can do that. These are not prime. ठीक है? But then we will repeat the same process for that. So then we get x is common to minus z mod p. So now look at 2xp. 2xp is xp plus xp. And modulo p, xp is yp. So it's xp plus yp. But xp plus yp is zp. So this is common to zp. But zp is minus x. So this is minus xp. So 2xp common to minus xp mod p. So 3xp common to 0 mod p. But p doesn't divide x. So p doesn't divide x per p. So p divides 3. But what? P is greater than 3. Contradiction. We have finished proving Fermat's last theorem for case 1. Modulo what? Modulo the fact that this is UFT. You can do some other stuff for case 2 as well. Point being, this states that it's not true that z adjoint a pth root of unity is a UFT. It is not true for all primes p. It's in fact the first prime for which it fails is 23, and there are plenty more for which it fails. So what do you do? That was the question. So what Kama did was what is the point of unique factorization in my proof for last theorem? Of course, it's a very sad thing that unique factorization fails, and we should ask ourselves why. But let's try to salvage this proof. I needed this ring to be a unique factorization domain to show that x plus y omega is u alpha bar. Can I show this in some other way? That was the question. Okay. So, I don't know whether I should show it this time. It will take me quite a bit of time. But the fact is, and this is what I mentioned earlier, it's a marvelous fact that if instead of factorizing x bar p plus y bar p is equal to z bar p in terms of numbers in z omega, let's try to factorize the ideal z bar p in terms of ideals. Let's say I1, I2, let's say up to ik into prime ideals. This turns out to be unique. This is a unique factorization. And for certain primes, which we call regular primes, which Kama called regular primes in fact, we can show that these prime ideals are principal ideals. Principal ideals meaning they are generated by exactly one element. So actually, it turns out that if instead of thinking that these are brackets, just think that I am calculating the ideal generated by x plus y times the ideal generated by x plus wy times the ideal generated by x plus omega p raised to minus 1 to y. Then this is equal to the ideal generated by z bar p. This turns out to be true. Okay? So then you are in luck. Because then the same proof actually follows through. You can actually, with minor changes, since you are actually having principal ideals generated by one element, much of whatever we did over here, it actually follows through. Because you can take modulo p in a very similar way. And thus, you have managed to salvage most of this for all primes which are regular, which I will now define. Okay. So, throughout this, where is it? It's a definition of a regular prime.
Okay, so someone proved that this factorization into prime ideals is unique.
Yes. Dedekind was not proved that. Factorization into prime ideals is unique. So, what is a regular prime? Let's see. For that, I need to make another definition, which is the heart of algebraic number theory, okay, and in fact of class field theory. So, this is highly not clear. By the way, I mentioned what is an ideal last time. For those of you who are not here, this is what an ideal is. An ideal is a subset of a ring. R is a general ring. Okay? Ring meaning there is additional multiplication. This is what I suppose. Okay? An ideal is a subset of a ring which satisfies certain properties. That is, first of all, it's a subgroup. I is a subgroup. Again, subgroup meaning it's closed under addition and taking additive inverses. Okay, as a subgroup. And if you take any, let's call it R in R and any A in I, then RA belongs to I. It's closed under multiplication by elements of R. Okay, so what are examples of that? Let's take the ring of interest Z. What are ideals in Z? Think of all even integers. I'll call that 2Z. Obviously, this is a group. You can add any two even integers and get an even integer. If you take any element in Z, any integer, and multiply it to an even integer, will you get an even integer? Yeah. So this is an ideal. Similarly, in fact, all ideals in Z look like nz, n times z, all multiples of n. Take any multiple of n, multiply by any integer, you are still getting a multiple of n. So all the ideals of Z look like nz. In fact, these are principal ideals. So since I am writing it in this way, I actually mean that it's generated by n. How do I generate an ideal out of an element? I simply take all elements in my ring and multiply it with this. So the ideal generated for in the general scenario, let's say R naught is in R. Okay, the ideal generated by R naught is nothing but the set of R times R naught, where R comes from R. Okay. This is how I generate an ideal. You can check that this is an ideal by this definition. You take any element from the ring, multiply by any element of this form, you get another element of this form. If you add any two elements of this form, you get another element of this form. Right? So this is in fact a subgroup and it's closed under R. So I have actually given a definition which results in an ideal. Yeah. This is what an ideal is. And where was I coming in? Yes. Regular prime. So I need to give a definition for regular primes. Yes. So what I'm going to do is I'm going to define an equivalence relation on the set of our ideals. Okay. You can think of Z omega or you can think of any ring in general. Okay. It doesn't matter. I will say the two ideals of this ring are equivalent if and only if there exist non-zero integers. You can call them integers actually, rather than elements of. Exist non-zero elements in my ring Z omega such that alpha A equals beta B. समझा क्या? मैं पता है इक्विवेलेंस रिलेशन होता क्या? रिफ्लेक्सिव सिमेट्रिक ट्रांजिटिव. We could actually have a long discussion on integrities of equivalence relation, but let's proceed. We keep that for another aspect. So, is this an equivalence relation? Is A related to A? Yo, because you can just take one. One times A is of course A and A is equal to A. And if A is related to B, is B related to A? Yes, of course. If A is related to B and B is related to C, then C is related to C. If A is related to B, that means there exists alpha beta such that alpha A equals beta B, and there exists another two elements, let's say that alpha prime B equals beta prime C. Then what element would exist is that alpha A equals beta prime C? Such that something A equals something C?
We just beta alpha prime alpha A is equal to
Alpha A equals
beta prime beta C.
beta prime beta C. Exactly. Beta B equals beta prime beta C. Yes, that's true.
Cancel B.
Okay.
कुछ नहीं. मैं कह रहा था कि ऐसा सोचा होगा. B दोनों तरफ से.
In fact, I'll tell you, you're not very far from being wrong actually, from being right. Because this can be thought of as every element in B is some fraction of an element in A. So you're taking two non-zero elements in Z omega, taking their ratio, which means you're moving to its quotient field. For those of you who know what I'm talking about. जैसे Z से हम Q में कैसे जाते हैं, वैसे कोई भी अगर अच्छा रिंग लिया, which is a domain, okay, then you can move from that to its quotient field. Take all possible ratios. That actually forms a field that are appropriate or similar kind of addition and multiplication. So actually, what you're taking an element out of that quotient ring and you're saying this ring looks like some fraction of this ring, some fraction multiple times this ring. These are all crucial ideas. Your intuition was not very wrong actually. Fine. So this is an equivalence relation. If I have an equivalence relation, then I have partitioned my set of all ideals into equivalence classes. It is a fact, non-trivial fact, that the set of equivalence classes are finite. Okay. And I will call H to be the order, the number of such equivalence classes.
What basically are equivalence classes?
Equivalence classes. So this entire set S, whatever it looks like, I don't know what it looks like. Under this equivalence relation, 2 points I will call them the same, or I will put them in the same box if they are equivalent. So having an equivalence relation allows me to create such boxes. If I didn't have an equivalence relation, maybe my boxes would overlap. But having an equivalence relation, I can actually partition my set into boxes, distinct boxes. where any two elements over here are related to each other, and if two elements are related, then they must be in the same box. I am saying that the number of such boxes are finite in this particular scenario. It's not at all clear why, and it's a very important result, and one which I enjoyed proving in my guess project. That the class number, this is guy, the number of classes equals as I'm calling H. It's called the class number. Class number of this particular array. Okay. And this is the main object of study, I think, in class field theory. If I'm not wrong, maybe upward. I'll now the definition of what a regular prime is. A prime P is said to be regular if and only if P does not divide H. So this is your definition. And it's quite easy to show that if this is the scenario that you have a regular prime, then it follows that these ideals into which I divided it, I managed to factorize this into, these are principal ideals. An ideal could be generated by more than one element. That is, it's not necessary that if I give you an ideal, it has to be generated by exactly one element. It's possible that it cannot be generated by exactly one element, you need at least two or three or something like that. It's possible. But if you have a regular prime, then you can show that under this factorization, you will be able to, you will have principal ideals. Principal ideals meaning they are generated by one. And once that is there, the rest of your proof follows and the proof follows.
Does it take into account all the primes which are left out?
Regular primes? That's a very good question. So, unfortunately, no. We know that there are infinitely many irregular primes. Okay. Even more sadly, we do not even know that there are infinitely many regular primes.
So our proof will not
Highly incomplete. But the fact is, there's a lot of beautiful things which has come out of this study. Point was, of course, not really to prove Fermat's last theorem in the maths club. I'm not so foolish. Greater men than me have tried that and failed. So the point was to give you motivation for the kind of concepts which are falling out of this. Unit factorization is a very beautiful concept, and the study of where, why, how it is failing, and how to salvage it, and how to work around it, that leads to very beautiful things. This class number is a very, very important option.
My question is why is factorization concept coming out
into 1 minus root of minus. Here, Q root of minus 23.
Minus 23.
Is 6 equals to 2.3.
Objects which we actually use like trace and discriminant, and talk in more abstract senses like all this discussion, because of the nature of the motivation, I am working in Z omega, in like another circularity. Instead, these same types of questions are asked in general for something, things called number fields, which are finite extensions of Q. So Q is a field, it is sitting inside C, I do not know. Have I told you this before? That, what is the number field and
Yeah. In last
time I told you. It won't hurt, I think, to make a quick revision of that. So Q is a field which is sitting inside C. You could, like how I adjoin elements there, I could possibly adjoin elements to this guy as well, A root 2. Set of all A plus B root 2 where it should be a rational. It turns out that this is also a field. You can verify, especially the axiom which shows that a manipulative inverse exists. That is not very clear why it should exist, but it does. So you can show these things. Q root 2 is a field, for example. Q iota is a field. Q root 2 root 3 is a field. Root 3. All these are fields which are sitting inside between Q and C. And you're creating them by adjoining 1, 2 or some finitely many elements. So these are finite extensions of Q. It's an extension field, right? So we call it a finite extension. And such finite extensions of Q within C are called number fields. And just as you have Z sitting inside Q, what is special about Z inside Q? Q is the fraction field of Z. Right? Similarly, for Q root 2, you have a fraction field. It turns out that it is Z adjoint root 2. In general, it is not true. For instance, for Q, I think Q adjoint root of minus 5, its fraction field is not Z root minus 5. Because minus 5 is component to 3 modulo 4. I think because of that, what happens is that its fraction field is, or is it 1? With 1, or I think one of these cases. Depending on whether this, whatever you have underneath the square root, it's component to either 1 or 3 modulo 4, you have that the ring of integers, that's what this is called, the ring of integers, to like correspond with this ring of integers. It's either this z root minus 5 or it's z1 plus root minus 5 by 2. It's either this or this. I don't remember the exact one, but you can prove these things. It's not very tough to prove stuff like that. It's very fun. And by square roots, you can take nth roots, you can take pth roots of 5.
Yeah, how did it find more than one insurance?
Actually, what you do is you take all possible polynomials in root 2 and root 3 with coefficients coming from rational numbers.
A plus root 2, B plus root 3, C, that form.
That is just a linear polynomial.
They are
Any
finite.
kind of polynomial.
ये स्टेटमेंट तो सही नहीं है ना, मतलब जैसे अगर 2 एलिमेंट लिखे हैं 3 एलिमेंट तो वो फाइनाइट होगा, ऐसा तो कुछ
नहीं, पर मैं रूट 2 रूट 3 पकड़ पास आया हूँ, सी से ही पकड़ लूँ, तो ठीक है। शिट, सी से नहीं, मुझे ए से लेना है, सॉरी यार। हाँ, सही।
क्योंकि मतलब
बिल्कुल। पर इससे क्यों
algebraic
पाई?
नहीं होना चाहिए।
हाँ, algebraic नहीं होना चाहिए। क्यों पाई है? Occurred exactly one element, but it's not a finite extension. Pi is not algebraic. There is no polynomial which pi satisfies. So polynomial with coefficients in Q which pi satisfies. It is highly surprising. Not all real. And there's no reason why that should happen, but it happens.
Can that infinite extensions?
Yeah, of course, add, for instance, no, I don't tell you. Create an infinite extension if you want.
But does it matter? Is it just?
It's not of our interest. Of course, people study them also, but it's not of our interest. We are interested in finite extensions.
But I mean, are infinite extensions special or they just?
Especially everything is special.
I mean, do they have some special properties?
Of course, it has some special properties. Everything has special properties. If something doesn't have any special property, that's a special property. Point is, yes, infinite extensions are also studied, but we are not studying. So this is all really interesting stuff and not at all very advanced. I could talk about this if you find it interesting. I could prepare better also. Actually, I don't have much stuff to tell you about it. So what did I do in that project? Maybe that I could tell you. What I did was I took the student's book, of course, and I read it from page to page. But apart from that, this is the order which topics went. So whatever I told you right now is just the very sufficient background which you need. So the first thing I showed was that the set of all algebraic numbers, means they are roots of polynomials with coefficients in Q. This is a field. Okay.
Everything is in C.
Yes, of course. This is in C. Yes, everything is in C. Set of all complex numbers which are roots of polynomials. That is, I'll call it A, and it's a field. I showed that it's a field. And of course, it contains Q because every rational is a solution to x minus that rational equal to 0. So Q is definitely contained in A, and this is contained in C. So hey, this is an extension field of Q. But unfortunately, fortunately or unfortunately, this turns out to be an infinite extension of Q. You can see why I'm sure.
A is which has all the algebraic numbers.
Yes.
अच्छा वो
Yes.
ठीक है ठीक है.
Yes. But this is an infinite extension. So this is too big for our purposes actually. Any field sitting inside between these actually, Q subset, let's say K, subset A. This guy, which is a finite extension, I'll call this to be a number field. What I showed was any number field can be written as Q adjoint a single element. So, in fact, such extensions they're called simple. That's called a simple extension. So, even better, I am interested only in finite extensions. In fact, all finite extensions are simple. Okay, what next? I also looked at the set B, which is the set of all algebraic integers. What are algebraic integers? Yes, that is excellent. But the definition which we make is algebraic integers are those numbers in C which are roots of polynomials over Z with monic polynomials over Z. So, for instance, 1/2. This is not an algebraic integer. Can you think of any monic polynomial which is satisfied by half? Or can you show that there is no monic polynomial with integer coefficient which is not satisfied by half? suppose there is a polynomial with rational coefficients x minus half, which is satisfied by half. Can you show that there is no monic polynomial with integer coefficients? Monic meaning its highest power, whatever it is there, its coefficient should be 1. That is monic. Can you show that it is not possible that half satisfies any such polynomial? That's an assignment for you. You can actually do that, it's not hard. But you have to try it. It's really not that doesn't mean it's not obvious. Doesn't mean it's obvious. Okay. So the integers, of course, though, they are a subset of B. And B is a ring. In fact, B, like how Gaurav suggested, it turns out to be the fraction field of A. Every algebraic number can be written as a ratio of algebraic field. But that is not my purpose. My purpose was in proving that it is a ring. But it's far more than a ring. It has a property which is called, something, right? One second. It's integrally closed. Yes. And this is immensely important. Integrally closed means you do this. Let's work it out in Z. Okay, Z is integrally closed. Let me say what this means.
B subfield है A का.
नहीं, सबरिंग है. B सबरिंग है.
Fractional field बोला ना.
A is the fraction field of B.
A is.
B ring है. B field बिल्कुल नहीं. So I say that Z is integrally closed. So what does that mean? Well, what is Z? Z is the set of all rational numbers which are solutions of polynomials with integer coefficients which are monic. That is, if you take any polynomial e of x, let's say, which is in zx, and it has a rational root, then the rational must be an integer. That's what I'm trying to say. Okay. Now we got z like that. Now consider a definition. It's integrally closed. Look at all polynomials. Now I'm confused. Wait. अभी जो भी बोल रहा ठीक है अभी जो भी बोला वो बोल रहा इस चालू करते हैं देखो what was B? B was a set of all complex numbers which are roots of polynomials over Z which are monic. Now you could consider polynomials over B itself. Consider polynomials whose coefficients are elements in B. There could be some elements in C which are solutions of this. Then you may be getting a bigger ring like B1. Then you can consider B1 polynomials over B1. And you can consider solutions over C over this. And you get something B2. ऐसे कर करके तुम आगे जा सकते हो ना? हो सकता है. At this point, maybe you are getting infinitely many rings, or you stop at a certain point. If you stop at a certain point, what does it mean? It means no new elements are coming out of it. Right? At that point, you call that ring integrally closed. It turns out that B itself is integrally closed. In other words, if you look at any polynomial with coefficients coming from B, which is monic, and then you look at any complex root of this polynomial, you will not get anything outside of B. You will still get only solutions which are any solution which is lying in B itself. So the set of all solutions of polynomials of this type which are monic, that is nothing but B itself. So nothing new is coming out, so it's integrally closed. That's the definition.
Where does this integral thing come? Integrally close क्यों बोलना?
क्योंकि Z की प्रॉपर्टी सेटिस्फाई करता है ना. Z की प्रॉपर्टी सेटिस्फाई करता है कि तुम Zx में कुछ भी हो. And look at solutions in Q in its fraction field. जैसे यहाँ पे भी हम एक्चुअली पूरे C में सर्च नहीं कर रहे थे, हम उसके fraction field A में सर्च कर रहे थे. So you look at Zx and look at solutions of such polynomials which are monic in Q. You can only get Z. That's what I'm saying. It's obvious to me. I don't know whether it's obvious to you. So since the integral satisfies this property. In some sense, they are closed under this operation. So we call it integrally closed. It's a definition which is actually very, very useful. Right? And there are many equivalent conditions to when something is integrally closed.
How is it different from algebraically closed?
What do you mean by algebraically closed?
Algebraically closed.
That a set is said to be algebraically closed
Thing is
if any polynomial over that
roots जो है वो
has a root within that same.
algebraic.
नहीं ना वो अलग हो गया तो हम यहाँ पे एक तो मोनिक पॉलीमॉर्फिज्म कंसीडर कर रहे हैं ओवर दी तो बेसिकली मोनिक पॉलीमॉर्फिज्म ओवर दी ठीक है don't we call algebraic closeness only for fields choose algebraic closeness यहाँ कोई भी रिंग के लिए भी बोल रहे हैं मुझे algebraic definition तो नहीं एक तो वही फर्क है कि ये रिंग है हम यूजुअली फील्ड्स के लिए बोलते हैं दूसरा चीज ये है कि हम लुकिंग एट मोनिक पॉलीमॉर्फिज्म ओवर सेट फॉर इंस्टेंस अगर यहाँ पे भी मोनिक हटा दिया देन ऑफ कोर्स 2x - 3 = 0 दिस इज satisfied by 3/2 so this is not satisfying what I'm telling. I want monic polynomials over Z. I'm looking for solutions in that over Q. You get on this end. So we are not getting anything new. Same will happen for this. So in that sense it is integrally closed. So ये हो गया. Point ये है, of course there is a definition तो बना गया. I need some equivalent formulations to make it workable. This way I cannot keep checking that मैं हर एक polynomial लूँगा B के ऊपर और फिर मैं देखूँगा कि क्या ये satisfy करता है कि नहीं करता है. I need another kind of way to check whether or not some element is integral, that is integral, or whether that set is integrally closed. So that comes from module theory. You'll be able to say something about the dimension of a module over the base ring and things like that. So that way you will see the merging of various different topics that you see, especially of rings and modules, because rings and modules में तुम जो भी पढ़ोगे ना वो सब बहुत बेकार लगेगा तुम्हें. ये सेंस में कि you feel like there's a lot of definitions going on, but nothing of substance. The reason for that is all those definitions are needed to do stuff like this, which is really, really interesting. But you don't really get down into the proper business when you're doing the course of rings and modules. Modules बहुत ज़्यादा beautiful subject है तो हर जगह, पर वो course बहुत बेकार है. So if you want to take up further reading like this, you'll be able to see अच्छा यहाँ पे आ रहा है, अच्छा यहाँ पे आ रहा है. तो वो लोग feeling आएगा ना तो बहुत अच्छा लगेगा. So apart from that, you'll never see rings and modules being used anywhere like this. It's only in their applications that they are very good. Otherwise, group theory by itself is actually very good. Group theory के लिए हमने ऐसा नहीं कह सकता. So immediately you can see that there's so much symmetry going on in the background. It's very beautiful by itself, but rings and modules by itself, there does not seem to be any motivation in the way the course is designed, other than just to generalize already beautiful. Paper operation पे दिया तो जैसे तुम्हें मेथड आइसोमॉर्फिज्म थ्योरम्स किया होगा, फर्स्ट आइसोमॉर्फिज्म थ्योरम ऐसे ही रिंग्स के लिए भी, उसके बाद तुम चाइनीज से मतलब थ्योरम यहाँ पे ये लोग pretty much the same thing. And मॉड्यूल्स में भी वैसे ही होगा ऑलमोस्ट. टेंसर प्रोडक्ट्स कुछ नया आएगा, मे बी कुछ डायरेक्ट नहीं, वो प्रोजेक्टिव फॉर्मूल्स वगैरह वो सब तुम पढ़ोगे, पर फील्ड तब तक नहीं आएगा जब तुम ऐसे कुछ एप्लीकेशन सीखोगे. हाँ, आफ्टर दिस व्हाट डू? Take some interesting things like what do I mean by the norm of an element, what do I mean by trace of an element, what do I mean by discriminant of a basis, and what do I mean by एक और था नॉन ट्रेस डिस्क्रिमिनेंट कुछ और था, उसको मैं शायद डेल्टा बोलूँ. तुमने किया है ना ये सब फील्ड्स नहीं किया है?
नॉन ट्रेस
पक्का
किस चीज का नाम क्या ट्रेस?
तुम अगर एक algebraic extension में हो, then you pick an element over here, the norm of an element alpha over here over Q, let's say. See, if alpha is in K and K is a number field, then it's an algebraic element, which means that there is a minimal polynomial which it satisfies. Which means there are other numbers which are roots of the same polynomial. The norm is the product of all those numbers. The trace is the sum of all those numbers. sum and product of the roots of the minimal polynomial of alpha. नहीं किया है, come on, तुमने कैसे, तुमने तो प्रूव किया था, तुमने बोला था
क्या?
कुछ तो इम्पोर्टेंट थियरम किया था ना, वो fifth degree polynomial is not you cannot write every element as in terms of radicals for fifth degree. वो नहीं किया, वो भी नहीं किया.
क्या नहीं है?
अरे यार इसमें क्या किया तुमने?
नहीं, नॉन ट्री मतलब हम लोग ज़्यादातर चीज़ें एल्जेब्रिकली उससे पढ़ रहे हैं, मतलब ये कंप्यूटेशन से कुछ नहीं है, मतलब ट्रेस निकालना
नहीं.
और सर ने मतलब स्टार्टिंग में बिगनिंग में थोड़ा वो बताया था, क्या कहते हैं, कार्डानोस फॉर्मूला वगैरह,
हाँ
थोड़ा एलिमेंट्री था, बस वो नहीं है, फिर सीधे हम तो एल्जेब्रा पे जंप किया.
चलो ठीक है, पढ़ोगे सर, मजा आएगा. Especially तुम जब जनरल कॉन्टेक्स्ट में पढ़ोगे, Stewart's book is really good for an introduction, but not once you actually get down to the अगर तुमने फील्ड थियरी पढ़ लिया तो फिर वो मत पढ़ना, तुम डायनेमिक मार्केट सीख लेना, ठीक है. If you have not seen any rings and modules, you should pick up Stewart's book. He manages to provide all the information without really getting into what is a ring, what is a module, which is and he says everything that needs to be said. So do take a look at Stewart's book.
तो बहुत ज़्यादा एल्जेब्रा चलेगा मतलब तो
आपका अभी का मैंने लिया था क्या भैया?
हाँ?
अभी का
नहीं ना, अभी चल रहा है कपड़ा से काम. उसके बाद क्या कर रहा है?
प्लस रेट
हाँ, उसके बाद मैंने स्पेसिफिक कंपटीशंस किया था. मैंने एक्चुअली एक अलग अलग तरीके के नंबर फील्ड्स लिए और देखा कि हाउ कैन आई यूज दिस काइंड ऑफ टूल्स टू फिगर आउट व्हाट इज इट्स रिंग ऑफ इंटीग्रल्स, लाइक एक्चुअली सिट एंड कंप्यूट. सो आई डिड दैट. मुश्किल है पर हाँ, एल्गोरिथम के थ्रू आप यूज कर सकते हैं, तो वो मैंने किया. फिर हमने स्पेसिफिक केसेस लिया कि k is equal to q, let's say square root of d, where d is a square free integer, तो नेगेटिव भी हो सकता है. तो इसका क्या है रिंग ऑफ इंटीग्रल्स? फिर आर्बिट्ररी एलिमेंट का नाम क्या, उसका ट्रेस क्या, उसका डिस्क्रिमिनेंट वगैरह वगैरह. ठीक है सर. In fact, there is a very famous conjecture by Gauss that there was a famous conjecture which was recently, as recently as 1950, पता नहीं, कि when is this a unique factorization domain? Gauss ने बोला था कि सिर्फ और सिर्फ जब d is equal to -2, -3, -5, -7, -17, -50 something, 56 ऐसा कुछ पता नहीं, and -163. These are actually pretty special numbers. सिर्फ और सिर्फ जब d ये है और नेगेटिव है तब यूनिक फैक्टराइजेशन डोमेन होगा. इसका क्या, ऑफ कोर्स नॉट प्योर डी, इसका जो रिंग ऑफ इंटीग्रल्स है मे बी z root d और दूसरा रिंग जो है z1 plus root d. So its ring of integrals is a u of d if and only if you have these finitely many things. गॉस के कंजक्चर थोड़ा गड़बड़ होता है शुरू करने में, तो फाइनली हो गया. एक और कंजक्चर था उसका कि देयर आर इन्फिनिटली मेनी d फॉर d पॉजिटिव, जिसके लिए u of d है उसका रिंग ऑफ इंटीग्रल्स, जो अब तक अनरिजॉल्व्ड है. But there is strong evidence for it to be true. This heuristic method, what I'm talking about is heuristic method. So you are saying that on average, it turns out that the proportion of positive integers for which this is a u of d, z root d or z1 plus root d by 2 as appropriate. The proportion of such d for which it is a u of d is approximately 33%. And I'm talking about overall integers. So there are results like that. You can study things like that also. There are papers on this. So it's awesome. And the theory of, especially the theory for these are called quadratic extensions, comes from studying quadratic forms. जो भी मैंने किया था, मैंने ये भी पढ़ा था, उसमें बहुत मजा आया था. And quadratic forms पढ़ते पढ़ते fundamental domains in complex plane ये भी आया था. And
फंडामेंटल डोमेन वही वाला है.
so you're seeing analysis creep in, and of course analysis creeps in studying class numbers. There are analytic formulas to do the class number. Can you imagine that? Class number is an object which is highly algebraic, but then there is a formula which involves a Riemann zeta function, which allows you to compute the class number. It's not simple. It's actually a functional equation. So you have on this side some sort of limit. As something goes to infinity of some terms, this is equal to something finite, and inside sitting over here, one of those terms is your class number. So if you manage to solve this, then you find out exactly what the class number is. And for small cases, you can actually use this to figure out what the class number should be. You get a nice bound. It should be between let's say 0 and 25. Then you can check exactly how many equivalence classes you get. You don't need to check for infinity. Yeah, possibility का check. So all this is really deep theory which is going on. पता नहीं मैं बोर्ड में क्या बन गया, ठीक है?
It is actually good also. Very good.
I didn't get time to actually go into stuff like this, but you can also do it. There are very readable books which give you algorithms to compute several of these numbers. And the fact is, many unresolved conjectures on how the class number behaves, that is, in what proportion they are existing. And for instance, it turns out that the class number is more composite than if you pick numbers at random. If you pick numbers at random in the same proportion as the class numbers are, then if you compare these two sets, in terms of the class numbers tend to be more composite. What that means is, you can use that kind of knowledge to provide an algorithm for factorization. This is quite fast, faster than digits. Of course, since it's a conjecture, you don't know it's true, so your algorithm may or may not properly factorize your number. But this is awesome. And of course, it's still a conjecture. So who gave it? I forgot the names. There are a couple of mathematicians who gave up heuristics on the calculation of class. It's a very readable paper. You can also do it.
क्या पूछा? कितने अनसॉल्व्ड कंजक्चर्स हैं? इन्फिनिट सेट नहीं
काउंटेबल है जो भी
बट काउंटेबल इन्फिनिट बट काउंटेबल। भैया ए और बी यहाँ पे कोई भी आर्बिट्री सेट से ए और बी क्या है यहाँ पे?
ये आइडियल्स।
अच्छा, आइडियल्स थे किन्हीं जनरल लिंक्स के?
तुमने एक रिंग फिक्स किया, इन पर्टिकुलर तुम ऐसे एक रिंग ऑफ इंटीजर्स लेते हो, एक नंबर फील्ड लिया, उसका एक रिंग ऑफ इंटीजर्स है, उसके जो आइडियल्स हैं, उस पे तुम्हें इक्विवेलेंस क्लास बनाना है।
नंबर फील्ड।
हाँ,
नंबर्स में।
हाँ।
मैंने कहा अगर आर्बिट्री सेट्स होते तो एक कितना अच्छा होता। इक्विवेलेंस क्लासेस और सब कुछ।
So after developing that sufficient number of amount of theory, I showed this where I could do that. Why did I do that? मैं बस एक चीज करके छोड़ देता हूँ. 11:15 हो गया. I'll show you some examples where doing factorization fails. ठीक है? And then तुम्हें शायद feel आएगा. Stuart in town.
कितने आदमी थे?
हाँ, इसके बाद ये a lot of geometry also comes into this, because first of all, those who attended my lecture last time, they know that I showed that Gaussian set of all Gaussian integers. This was a principal ideal domain. That's what I showed. I showed that this is a PID. Because it's a PID, it's a UFD. मैंने प्रूव किया. तो PID मैंने कैसे किया था? I actually took I embedded the Gaussian integrals into the complex plane. Because how would they look like when you embed it into the Gaussian plane? We're looking at all integer points.
Oh.
So it's kind of a lattice.
Yes.
So you have a lattice. What I want to show is that every ideal is principal. Right? So to do that, what I did was take an ideal. And I use the norm, which I told you. The norm of an element of the form x plus iota y is x squared plus y squared. So what is that in the complex plane? It is distance kind of, right? So, and it's an integer. So there will be some element in your ideal, since the ideal is non-zero, which has minimal norm. My claim is that ideal has to be generated by that one element. That was what I did. समझा क्या हो रहा है? कि मैं अगर एक ऐसा एलिमेंट लूँगा, think of it now in terms of the lattice. मैंने एक definition लिखा था. What does it mean for you to generate an ideal out of an element? But if you think about it in terms of the lattice visualization, you take an element. First, you have to consider subgroup out of this, right? So if you took an element, a lattice point like this, then every integral multiple of it like this and like this must exist. But any iota times that must also exist. So iota times means this will exist, but then any multiple of this will also exist. So you've got all integral points in this direction, or integral points in this direction, and you've got any multiples of any addition of elements over here. So do you see how the lattice is generated? Every point in the middle is also coming up. So you took one vector and you constructed a lattice out of that. Claim is that this is the complete ideal. Why was this the complete ideal? I'm not able to give the full picture because I'm too lazy to work this out. I'm so sorry. If it's not the complete idea, there is another element somewhere which is not sitting on this lattice. But if it's not sitting on this lattice, then it's somewhere in the middle. What is the distance between that point and a lattice point? It will be smaller than the length of this of the side, right? But if the length of this, if it's smaller than the length of the side, then
the minimum.
the original element you took was not the one with the smallest one. This element is the one with the smallest one. So you arrive at the contribution. So that was I don't know whether that is clear. Sorry. So sorry. I'm so sorry. I'm rushing. I'm so sorry. कहाँ है मेरे एग्जाम्पल्स ये लेके मैं छोड़ देता हूँ
सब लोग जल्दी सो जाते हैं क्या? श्रेया
श्रेया
जल्दी